So welcome to our MOOC on magnetic resonance. This is now the second half of chapter 3, where we shall be speaking more about spin-spin couplings. We should now address a tricky issue of equivalent nuclei. It turns out, and this is very nicely described in Peter Hoare's book, I think it's one of the best books on this subject, there are two forms of equivalence. There is chemical equivalence, that's fairly easy to understand. That means that you have two nuclei that cannot be distinguished in chemical terms. One cannot substitute one without substituting the other. One cannot replace one cannot conceive of a reaction that would affect one without affecting the other. That's one thing. And then there is the concept of magnetic equivalence, which is much more subtle and more difficult to define. But let us start with a simple application. First of all, we have this magnetic equivalent pair here, where these two protons have the same coupling with the two fluorines. So if we take this coupling here, or this coupling here, it turns out that by symmetry of this molecule, these two couplings are the same. Likewise, if we started with the two fluorines, they also have the same couplings to the two protons. But this is not so these two here are the same. But if we look at this coupling here, which is a cis coupling, it's different, in different magnitude, or perhaps even a different sign, from this long-range coupling here, the trans coupling. So this is distinct from this. And therefore, there are two different cases. Well, it turns out that Peter Hoare has a wonderful way of explaining how you can check for the existence of magnetic equivalent nuclei. First of all, you define an ensemble of nuclei A, B, C, etc., of nuclei of which you want to decide whether they are magnetically equivalent or not, such as in this case proton A and proton B. And then you define external nuclei, if they exist, like in this case, this fluorine, which we call Z, or rather Peter Hoare uses that nomenclature. And then he says, if the J coupling between A and Z is equal to the J coupling between B and Z, is equal to the J coupling between C and Z, and all similar things, in that case we have magnetic equivalence. And if that is not the case, as in this molecule here, then we have only chemical equivalence. We shall see in spectra that has dramatic consequences. Now, this test here, where we compare the scalar couplings between A, B, C and an external nucleus Z, in principle has to be repeated for different external nuclei. For example, we once do it for Z, and then we have to do it all over again for the nucleus Z prime. In practice, it turns out that once you have a negative answer for one of them, you don't need to check the others, but magnetic equivalence needs to be thought about quite carefully. Now, there are cases which are not obvious. For example, this is dodecahedrane, has the molecular formula C20H20. If all carbons are C12, which is not obvious, but if it's depleted in carbon-13, then we have no other nuclei than the 20 chemically equivalent protons. And so there is no Z, there is no external nucleus Z, and consequently we can't conduct the test, and it turns out that all 20 protons are magnetically equivalent and not only chemically equivalent. The same is true on a much more mundane molecule, which is that of benzene. There we have 6 benzene protons, as you all know, and in this case they're all equivalent because there is no proton Z or no carbon Z that could prove that they are inequivalent. Now, multiplet patterns can be used to check for molecular symmetry or to confirm or reject a hypothesis about the symmetry of a molecule. And Peter Hoare has collected some wonderful examples for phosphorus-31 NMR spectra in these compounds which contain only phosphorus and sulfur. So the large spheres represent the phosphor atoms and the small spheres the sulfur atoms, and you can see there can be different arrangements. And it turns out that sulfur has no spin, at least the dominant isotope has 99%, abundant has no spin, and therefore we can ignore it, and we only have to worry about the chemical shifts and about the equivalence, chemical or magnetic equivalence of the phosphorus nuclei. So it turns out that in a configuration like this, again, there is no atom Z, there's no nucleus Z that could be conceivably have different couplings with the different A nuclei, the 4 phosphorus nuclei. And therefore, it turns out that these 4 A's are in the same environment, they're chemically indistinguishable, and furthermore, they are magnetically equivalent, and therefore we call them A4. This system has a different symmetry. You immediately see that these two nuclei these phosphorus are sitting between 3 sulfurs, whereas these phosphorus nuclei have another phosphorus for neighbor and then only 2 sulfurs as neighbor, so chemically they're quite different. In fact, they also have different chemical shifts, but when it comes to the symmetry, it turns out that the coupling between one of these A's and the 2 X's is equal, and so we have an A2X2 system. And the result of that is that on the A side we have a triplet, and on the X side we also have a triplet. This is a more complicated case where this phosphorus on top here has 3 sulfurs, a bit like what we had before, but at the bottom here we have a phosphorus which is squeezed between 2 other phosphorus, whereas the other phosphorus are squeezed between a phosphorus and 2 sulfurs. So clearly we have 3 different chemical environments, and it turns out that we have an AMX2 system, because the only equivalence, the only magnetic equivalence is between these 2 X nuclei, and the consequences are, as you can see, for example here in the A multiplet we have a large triplet due to the coupling between A and X. The X are the neighboring phosphorus nuclei, and a smaller coupling, JAM, between the A and the distant M nucleus. So this is a wonderful example on how we can look at the spectra and draw conclusions as to the symmetry of the molecule. Now, there are also amusing cases when we look at lithium-7, or lithium-6 is also an interesting case, but lithium-7 has a spin 3 halves. And this is a little bit like boron-11 that we have discussed before. In this case, we consider a strange molecule, which is actually a cluster comprising 4 lithium atoms arranged according to a tetrahedron. And it turns out that you can attach these tertial butyl groups, and that they are not attached to one of the lithium atoms, but they tend to attach themselves to the middle of the triangular surface of one of these sides of the cluster. Very mysterious chemistry, but the NMR is without any doubt proving that this structure is the true structure and not the one that you might intuitively draw. Well, it turns out that because of this structure, if we look at the lithium spectrum, lithium-7 spectrum, which as I said has a spin 3 halves, we shall see an ordinary binomial quartet because of the splitting to 3 equivalent carbon-13, which are, so each lithium in effect sees 3 carbons. For example, if we take this lithium here at the top here, it sees this carbon-13 and this carbon-13 and this carbon-13 as equivalent. And therefore we have this wonderful quartet. On the other hand, we could also decide to enrich this cluster with lithium-6. Lithium-6 has spin 1, so it will split its neighboring carbon into 3 equivalent lines with amplitude 1 to 1 to 1. But then it turns out that each lithium is, each carbon, is coupled to 3 lithium nuclei, and therefore gives rise to this very strange non-binomial multiplet, which is comprised of 3 interleaved triplets. So I vividly recommend you to look at this. This is in fact similar to what you have seen in diborane, except that now it's a coupling to 3 neighboring nuclei. In 4-spin systems, we have more complicated structures, as you might expect, but they're fairly easy to rationalize. In fact, we can simply take the proton NMR spectrum of dibromo-nitrobenzene. This is, of course, a very simple molecule. And we can see that we have here a proton A, which is squeezed between a proton P and a proton M. The couplings here, the orthocouplings, are not exactly equal, though they are similar. And then we have this X here, which is across the ring, so to speak, and that will have a long-range para coupling to the A and medium range to the meta positions P and M. And as a result, the A multiplet will be split into what's sometimes called a pseudo-triplet. In fact, it's just a doublet of doublets with very closely related couplings. And there's a fine structure, which is a doublet, which is due to the para position X. The M, on the other hand, is split into a large coupling because of the JAM, and then each line is split into a doublet and again into a doublet, first because of P and then because of X. Likewise, the same logic applies to spin P, which is very similar to spin M as far as the structure of the multiplet is concerned. And finally, spin X is a pseudo-triplet because of almost equivalent couplings to P and to M. And each component is split into a small doublet because of the para-coupling between X and M. This kind of spectrum can allow you to determine this molecular structure almost without any other help. There is an interesting phenomenon in scalar-coupled multiplets, and this is known as strong coupling, or sometimes known as second-order coupling. And you can see that we have a system that evolves from a case where the splitting here, the J splitting, is much smaller than the difference in chemical shifts. And in this case, we speak of an AX system. But when the chemical shifts come closer, then we notice that the multiplets not only become closer, as you might expect, but they change the amplitude ratios here. The inner lines become stronger and the outer lines become weaker. And in a case like that, we use two letters in the alphabet, which are closer together, and we speak of an 8B system. And ultimately, if the two chemical shifts become degenerate, in fact, we have only one line over and then left over, and then we speak of an A2 system. So, to understand strong coupling, we have to use a little bit of quantum mechanics. This is not treated in any detail in the first volume of Peter Hall that I recommended to you, but there is a second book that you may wish to read in a year from now maybe, that is written by Steve Wimperis and Jeremy Jones and the same Peter Hall in the same series, the Oxford Primer series, and that speaks about such quantum mechanic effects. Well, in this case you should know that we have to explain the case where we have the AX system where we have just two doublets, we have the AB system where the two doublets move close together so that the inner lines become more intense, and the case of the A2 system. It turns out that all three can be explained in one equation by saying that the bottom state, that's this one here, where the two spins are parallel with the magnetic field, is not affected by this phenomenon. So they are always the same. It's always a simple state with alpha alpha. Likewise, the upper state here, where the two spins are anti-parallel, is unaffected. It doesn't matter whether the system is strongly or weakly coupled. But the intermediate states, called psi2 and psi3, they are mixed. And in fact, they are neither alpha beta nor beta alpha, but there is a wonderful admixture between these two, and the coefficients are cosine of an angle chi and sine of an angle chi. Now, this angle actually is determined by the ratio of the J coupling and the difference in chemical shifts. So to draw this in sort of simple trigonometry, if we draw the chemical shift horizontally like this, so this would be a number in Hertz, and if we draw the scalar coupling vertically, also a number in Hertz, then we can make a little diagram like this, and we can have this line here, and this angle here is 2 psi. So you can immediately see when the J coupling goes to 0 or becomes much smaller than the difference in chemical shifts, then psi goes to 0. So the limit of psi going to 0 means that if we take state psi2, the cosine goes to 1 and the sine goes to 0, and this is a pure alpha beta, alpha for spin A and beta for spin B. And likewise, if we take the limit of psi going to 0 for psi3, then only the cosine term survives, so this would be a pure state where spin A is in beta polarization and spin B is in the alpha polarization. So you can see from this diagram that the larger J compared to the difference in chemical shifts, the steeper the slope, the closer this angle to xi approaches 90 degree, and therefore the angle xi turns to 45 degree. It's therefore interesting to see the limit when xi goes to 45 degree. We see from this equation that the cosine and the sine become equal, and so if that we take that function, then it's just 1 over square root of 2 alpha beta plus beta alpha. Likewise, the limit for xi going to 45 degrees, so this is still the case where this J coupling is much larger than the difference in chemical shift of the other function, goes to 1 over square root of 2, and here we have minus alpha beta plus beta alpha. Now you notice that in the case of the A2, you see there is this symmetrical linear combination, which is what we have here. This is symmetrical in the sense that if you do a permutation of spins A and B, this wave function doesn't change. It is invariant to a permutation and is known as totally symmetric. Whereas the other wave function, this one here, that's the one that I just concocted up here, is anti-symmetric with respect to permutation of the spins. It turns out that this first state, together with the top state and the bottom state, that these three together form what is known as a triplet. That is to say, three states of the same symmetry, whereas this guy here is known as a singlet. And the remarkable thing is that now the intensity that we see here in the spectrum is made up of two lines, only two lines, that are degenerate and occur on top of each other. One corresponds to this transition to the middle component of the triplet, and the other line corresponds to the top transition within the triplet. Whereas the transitions from the bottom line to the singlet are forbidden, so that's represented by this dotted line, and I cross it out to show that these two transitions are completely forbidden. In fact, they are here virtually, so to speak. If you look at their frequencies, they are plus or minus J away from the central component, but their intensities are vanishingly weak, and that is why we cannot see them. This kind of quantum mechanics has been known for decades, but it has gained some renewed interest very recently, because it turns out that the populations here flow quite freely within this triplet manifold as a result of what we shall call longitudinal or spin lattice relaxation, whereas the populations cannot, are locked in the singlet state and cannot flow from the singlet to the triplet state. So if one can contrive some way of populating the singlet state, then the populations would be locked in there, and one can have so-called long-lived states. This is a specialty of Malcolm Levitt in Southampton, and we have done a lot of work in Lausanne to try to improve techniques to populate these singlet states. This concludes part 2 of this chapter. Thank you for your attention.